Hi, everyone. 9.3. Okay, so let's recap. Chapter 8, all to do with confidence intervals and estimation. Chapter 9, all to do with hypothesis testing. So 9.1, intro to hypothesis testing, how to write a hypothesis, how to interpret a p-value, and how to conclude. 9.2 was all about proportion, so doing an entire hypothesis test from start to finish with proportions. And then 9.3 is going to be an entire hypothesis test from start to end with means. So it's all going to be about the means. So it's very, very similar to proportions. The only thing that's going to be slightly different would be your conditions and the how you calculate your test statistics. So random does not change. 10% does not change. There's our 10 times n has to be less than or equal to n. What does slightly change, and this is the same as it was for confidence intervals, is how you test for your normal or large sample. So there's kind of 3 different levels. So 1, the population tells you it's normal. You're done. It doesn't matter if you have 3 things. If your population is normal, you can assume normality. If it doesn't tell you that, then you're going to look to see if your sample size is large enough, which is n is greater than or equal to 30. And remember, this is only for means, not proportions. Proportions is different. If it is, if n is greater than or equal to 30, you're fine to assume normality. Good to go. If the population distribution has an unknown shape, so we don't know it's normal, and n is less than 30, we're going to use a graph to make sure that we don't have any strong skewness or outliers. Now, well, one more thing. How do you find your test statistic and your p-value? So I think we said this back in confidence intervals. Whenever you're dealing with a proportion, you're going to use the z statistic. Whenever you're dealing with means, you're going to use a t statistic and then a t-CDF. So here's how you calculate your t statistic. It's your sample mean minus your hypothesized mean over your standard deviation divided by the square root of n. Just like with the hypothesis test for proportions, you could have a one-tailed test or a two-tailed test. And then the one-tailed test is when you have, or this would be a right-tailed test, so it's a one-tailed test, but it's also right-tailed, if you have a greater than in the alternative. If you have a less than in the alternative, then you have a left-tailed test. And if you have a not equal to in the alternative, then you have a two-tailed test. And then as before in confidence intervals, degrees of freedom is n minus 1. Hold on. You're like, wait, she's already lost me. Go to your reference papers. Go to the second full page of the reference paper, and you can see it. There's a whole section on means. We are still working in one sample. Chapter 10 gets us into 2 samples, but for now we're still in 1 sample. So go to means, go to 1 sample. We are dealing with tests. Right here is those last 2 slides. Right here summarized for you. So you know whenever you're in the plan, you must name your test. There it is. 1 sample t-test for mu. Right there. Conditions, random, normal, independent, all right there. And then you can see the normal stuff. It tells you it's normal, or you have a large enough sample size, or you need to graph it. So you may want to just make a little note next to that that says graph it. And then when you calculate your t statistic, there's the formula. And then it does remind you that your degrees of freedom is n minus 1. And then to find your p-value, your probability, you will be using a t-CDF because this is a t statistic that you are using. So get used to using this reference paper, mark it up, write all over it, anything you think that is helpful at all. Okay, so I've got 2 examples, and then that is pretty much it. So with this one, we have the famous 6-inch sub dilemma. So is the 6-inch sub really 6 inches? So 2 students, Abby and Raquel, they went to the 6-inch sub shop, and they decided to randomly select 24 different times during the next month, and they ordered a 6-inch sub, and then they measured it. So here are the different measurements right here. There they are. And then this phrase right here, this is going to drive you nuts because it doesn't make any sense, but that's actually how it's asked. Do these data, so it should say does this, but it doesn't. It always says, do these data provide convincing evidence at the alpha equals 10% level that the sandwiches at this restaurant are shorter than advertised? So how do we show this? The first thing we do is we start with our state. we wish to test the following hypothesis at a 10% significance level. We have the null, h sub 0, that should be a sub 0, but it doesn't matter. Your null is that the mean equals 6, and your alternative is what they're trying to test, which is the mean is less than 6, where mu is equal to the average sub length. Plan. Name your test. We will use a one sample t-test for means. Talk about random. They randomly selected, they didn't select subs, they randomly selected times, I should say times. 10 times 24, assume that there are more than 240 subs made in that month, which there should be. Now, our dilemma comes with, our problem comes with the normal, our large counts, because there's only 24 lengths up here, and 24 is less than 30. They didn't tell us it was normal, and 24 is less than 30. So we need to graph this. So I did this on an Inspire, but you could do it on really any, I think you could do a dot plot if you just Google it, or just grab a calculator, whichever. If you have to do this, what I would recommend that you do, if you're in the classroom, is graph this on the graphing calculator, and then just take a picture of it and put it into the work just to show that you did graph it. As you can see with this graph, no strong skewness and no outliers, so we are good to proceed. Now, let's see if I can zoom in a little. I don't know if that helped at all, but here's my work for the test statistics. So I calculated the mean. So there's my data. I typed it all in the calculator. I found my mean and my sample standard deviation because it is a sample. So then I typed it into, or I inputted all those numbers into the test statistic. So our test statistic is your sample mean minus your hypothesized mean over the standard deviation divided by the square root of n. So it's all right there. And that little number right there says 0.66. I'll send on the calculator that gives you negative 2.38. Okay, so what I like to do at this point is draw what's going on here. So I always draw my normal curve. Negative 2.3 is going to be on this side of the curve. And yes, by the way, this is a really important step to draw. Don't forget 0 is always right in the center. Then you go back and you look at your alternative. In your alternative, there's a less than symbol. So that means I'm going to shade less than. Now what that does for me is it lets me do a TCDF pretty easily because I now know I'm going less than. What is less than? Well, it should be like negative infinity, but we use negative 10,000. Make sure these are labeled. So this would be your lower. This would be your upper. And that 23 right there, that represents your degrees of freedom. And degrees of freedom is n minus 1. Type that in on the calculator. Get your p-value, which is 0.013. Now you just compare that p-value with your alpha. So p, which equals 0.013, is less than alpha, which equals 0.10. So if p is small, you reject the null. So since p is less than alpha, we reject the null. If you reject the null, so you're going to say, we have convincing evidence that the average sublength is less than 6 inches. Okay? And then it said, given, oh, by the way, we should talk about interpreting the p-value. We've talked about this before, but your p-value is the probability that your null is true. So if the mean is actually 6 inches, then the probability that we get the sample statistics that we did, the probability that we get a mean of 5.68 and a standard deviation of 0.66 is 0.013. That is a weird and unusual probability, a low probability, so therefore the null is probably not true. For part B, it says, given your conclusion in part A, what type of a mistake, a type 1 or a type 2 error could you have made? So remember, type 2 is the easy one. That's the one where you fail to reject the null when you should have. And then type 1 would then be when you reject the null when you shouldn't have. You should have kept it. So since we rejected the null, we could have made a type 1 error, and that's that we could have found that the sublength is less than 6 inches, but it isn't. Okay, so pretty straightforward. That's a hypothesis test. Like I said, a lot of it is on the reference paper. You just kind of follow the steps down. It's the same steps as every other hypothesis test we'll ever do. With the state plan, do you conclude? Just depends on what goes in each section. And if you're ever not sure, you just come over to your reference paper, find the right section, and you will have it. Okay, last question, because I said I was only doing 2 examples. This one's slightly different. We're still going to be talking about means, but this time we're going to be finding the difference in means. So let's just read through this one. It's slightly different than the last one. So we've got Libby and we've got Catherine, and they want to investigate whether the express lane or the regular lane is faster. So to collect their data, they randomly selected 15 times during the week. They went to the same store and they bought the same item. So that right there is for replication, so that there couldn't be like a confounding variable. So let's say like one time they bought an item that ID had to be checked for. That might slow things down. Or maybe a bulkier box. So they bought the same item. They went to the same store for replication purposes. One of the students used the express lane and the other used the closest regular lane to decide which lane of them they would use. They flipped a coin and then they entered the lanes at the same time, paid with the same method, and recorded the time in seconds it took them to complete the transaction. Carry out a test to see if there's convincing evidence that the express lane is faster on average. Okay, so key thing here, someday when we get into 2 sample tests, you're going to wonder if this is a 2 sample test, but it's not, because each one is done at the same time. Okay, so it's like thinking the same thing is done to the same item. Another thing that'll give that away is when you see that difference column, because then that will usually conclude that you need to do a difference. So with this one here, we want to conclude that the express lane is faster. So the trickiest part here is writing your hypothesis. So the first one is easy. When you go to write your null, we write this one as mu sub d because it's the difference in the means. And if there's no difference between the 2 times, then their differences should be 0, right? If it's the same time in the regular as in the express, then their differences should be 0. The tricky part is figuring out what your alternative is. So it's still mu sub d because those symbols don't change. Oh, shouldn't have wrote an equal sign there. Sorry about that. Okay, so now when you subtract the regular lane minus the express lane, if this lane is faster, if the express lane is faster, then this should take less time and this should take more time. Does that make sense? Like the regular lane should take more time. The express lane should be faster, so it should take less time. If you subtract a number that's more minus a number that's less, you should get a positive number. So therefore, we are hypothesizing that our difference will be greater than 0. Okay, so let's back up because again, this is the trickiest part of the whole thing. Other than that, it's exactly the same as the last question. So we've got our regular lane, we've got our express lane, we've got our differences. So the first one, the regular lane, they are hypothesizing that the express lane is faster. If your express lane is faster, it means you take less time to go through it. It would take more time to go through the regular lane. And if you subtract more time minus less time, you should get a positive number. At some point, we might be able to do one. Let's just say that these were switched, even the order. So if this had been switched, you would have had less minus more, and that would be a negative number. And then that would switch what your symbol is up here. But given the order that we have right now, we're going to go with the top one. Again, you'll get some practice with this again later on. I may get confused with that. So just keep in mind that that's where those numbers came from. Okay, so we have state. We wish to test the following hypothesis. H sub 0, mu sub d, so it should be mu sub d, not ud, equals 0, and your alternative is that mu sub d is greater than 0 at alpha equals 0.05 significance, where mu is equal to the true mean difference between regular lane and the express lane. So again, eventually you're going to wonder whether this is a 2 sample or a 1 sample because we're only really concerned about the differences and it's very dependent, then we will be doing a one sample t-test for the difference between the means. Again, one sample t-test difference between the means. Make sure the first thing you do in plan is name your test. Second thing you're going to talk about random. They randomly selected 15 times during the week, and they also flipped a coin to determine which lane to use. There's no need for the 10% here. You can check it if you want to, but it's kind of unnecessary because you're sampling with replacement, if that makes any sense. But you could always check it, and you could say 15 times 10 is 150. So assume that there's more than 150 times that people could check out within that, what was it, a week or a month? A week. And then lastly, our normal large counts, we have another issue here. If you look down the list, there are only 15 times recorded, so they need to graph it. I could have graphed it. I did graph it at some point. I promise you there are no outliers or obvious skewness. So you're going to talk about outliers and skewness. There's no skewness. There's no outliers. It's fine. And again, I would have graphed only the differences. Okay, so only going to graph that third column because that's all I'm talking about here. And then that brings me to my next thing. When I get to the do column, I'm only finding the mean and the standard deviation for the differences, which I did on the calculator. Then that gives me my test statistic. So you do your mean, your sample mean, which is the 42.7, minus your hypothesized mean, which is 0. And then over the standard deviation divided by the square root of n gives me 1.97. So again, I always draw this. I'm going to have 1.97 over here because that came from there. Go back up to the alternative. In the alternative, there's a greater than symbol. So I'm going to shade greater than. So once I shade greater than, that tells me that this is my lower bound. This is my upper bound. And this is my degrees of freedom, which is n minus 1. Type that in on the calculator, and you get 0.03447. Now, there's a good chance that on the computer calculators, I didn't test this out, but I bet, remember, all this stuff is under second bars. It's your distribution. We want TCDF, which is option 6. Oh, it does give me lower and upper. Very good. Because I think it was binomial that didn't. You can type it in exactly as that's there. So 1.97. My upper is 10,000. My degrees of freedom is 14. And there's that number that I have there, the 0.03447. So as a review, that's where that came from. Okay, and then we compare P to alpha. P is 0.03, alpha is 0.05. If P is small, we reject the null. If you reject the null, there is convincing evidence that the express lane is faster on average. Okay, so like I said, everything's in the reference paper. No surprise, especially after you watch the previous video with proportions. Means is the same. It's just slightly different on how you calculate the test statistic. The p-value, you use a t-CDF instead of a normal CDF. And that large counts normal condition. Everything else is exactly the same. And then there is a slight difference between the regular one sample t-test and the difference of means. But like I said, usually they're going to give you a difference column, and they'll usually even give you the test or the statistics for the difference column. That's usually the key indicator that you're supposed to use a difference. Okay, so that actually finishes up Unit 9 for us, and we will be starting Unit 10 shortly. It's the exact same stuff, except for now we're going into two samples. So two sample proportion, two sample means, and we will be talking about confidence intervals and tests for both of those.